হ্যাঁ, মাইকটা হয়েছে, ক্যামেরাটা এখনো হয়নি। Camera cannot be enabled. I don't know.
I have already made you a presenter, but
Somehow the camera is not getting on.
in this
Even
device also.
in this device also. Even I cannot see it. In the other device, I could not see myself, but here I cannot open my camera at all. Let me try the sharing thing, at least if that works. Can you see my screen?
Yes, sir. We can see your screen.
Okay, so maybe we should just go ahead without wasting time. We should go ahead without the camera. I'm sorry, but it's not working. And also it's already 6:50. So what do you suggest?
Okay, fine.
It is not so important to see me. I mean, I think the talk is
So
more important.
can you try one more time on the, because I can see the camera is already turned off. If you try to click on that, so
Yeah, I'm turning on the camera, but somehow the camera is showing a problem.
okay.
It is trying I can see that no, it's not getting on.
Anyway, then, but it looks very awkward. But anyway, so you can start then, because all the participants are waiting, and yeah, so that would be
yeah. No issue. Yeah.
okay, fine.
I can send one of my photos later. You can share it so
Okay,
that
fine.
they know who talked, who gave the lecture.
Okay.
So yeah, this is my. So if you want to introduce or anything, I will just.
I have done that part when you were trying to connect, so you can start. Yes.
Okay. So thank you, and thank you for the technical glitches. Sorry about that. So I'm going to talk about something that actually, is very much related to this magnetic data storage and computational technology. So which is magnetization dynamics, and I will start from the theory to experiment. Let me switch on my pointer. Yes, okay. And my name is Anjan Barman. I'm a senior professor and dean faculty at the Department of Condensed Matter and Material Physics at the S.N. Bose National Center for Basic Sciences. So this is it's an old picture of our institute, and this is the bust of Professor Satyendranath Bose, and you probably know that he is well known for the Bose statistics, which was actually discovered in 1924 and in the Dhaka University. And the last year, 2024, we actually celebrated the 100 years of the centenary of Bose statistics. It is an autonomous educational and research institution. It's funded by Department of Science and Technology and the Government of India. We have a permanent faculty strength of 34, and we have other non-permanent and others faculty and other scientists about 30, and we have 200 PhD and master students. It is an integrated PhD and post-MSc PhD program. So we are primarily a research institute, and the outline of my talk today, because this is a spin-based technology, and I have been told that there may be, sort of BSc level students as well. So I will start with a very elementary introduction of spin angular momentum, and then I will move to challenges and applications in nanomagnetism and magnetization dynamics, and then I will give some theoretical backgrounds. I'll show the experimental techniques for the magnetization and magnetization dynamics, and I'll show you exemplary results with various techniques which are listed here. But before I describe them, there is no point in naming them. So I will go first to the spin angular momentum. So I think many of you have heard about Zeeman effect, which was discovered in 1896, where in presence of a magnetic field, the spectral line was splitted. And in order to explain it, Sommerfeld actually proposed in 1916 that the electrons will be based on 3 quantum numbers, n, k, and m. That is what he named, and that described the size of the orbit, n, the shape of the orbit, k, and m as the direction in which the orbit was pointing. This was initially successful and was able to qualitatively capture the Zeeman effect, but there was a problem at the weak magnetic field, which is also known as the anomalous Zeeman effect, and it failed to explain the anomalous Zeeman effect. Then in 1924, Wolfgang Pauli, you may have heard this name many times, he showed that the core electron angular momentum was not involved to this effect. And that has been previously assumed that both the core and outer shell angular electron angular momentum are involved, but rather only the light element electrons, which is the outer shell electrons, determine the angular momentum. And he hypothesized that this required a 4th quantum number with 2 valuedness, and this is known as the spin magnetic quantum number. Okay, so here you can see a picture of a spin half particle, which can be electron, and the projection of those on the z-axis. So this has a spin half, so it has a spin magnetic quantum number of ms plus half and minus half, and their projections on the z-axis are sort of h cut over 2 and minus h cut over 2. So it's an intrinsic angular momentum possessed by various fundamental particles like electrons, protons, and neutrons. And it is a quantum mechanical property. It has nothing to do with the particle's physical rotation or motion through space. Like the orbital angular momentum, as you know, it has to do with the particle's physical rotation or motion through space, whereas the spin is characterized by a quantum number, and it has nothing to do with the physical rotation. It has a quantum number that is associated with a magnetic moment, and particles with spins, they behave like tiny magnets. And for a given spin quantum number s, there will be 2s plus 1 possible spin states. So if s equals to 1, then there will be basically 3 possible spin states. S equals to half, there will be sort of 2 possible spin states, and so on. So it will be represented by the spin magnetic quantum number. So for spin half particle, there will be 2 states, spin up and spin down, like you can see here. And this has ms equals to plus half and minus half. So this spin property will be of paramount importance in the new technology of spintronics, which is also known as spin electronics, which uses not only the charge property of electron, but also the spin property of the spin degree of freedom of the electron. And that is why I describe, and also the magnetization of most of the magnetization in the magnetic materials are determined by this spin angular momentum. Why I said most? Because there is also diamagnetic property, and it has nothing to do with the spin angular momentum. So challenges in nanomagnetism, I took it from this review article in 2006, which shows that at this point of time, it hasn't changed much, although some additional things have been introduced, but the grand challenges in nanomagnetism remain the same. It starts from discovering ultra strong permanent magnets. This is still a very important area. And then ultra high density media, magnetic media. So magnetic storage you all use in your computer, in your sort of external hard drive, and many other places. And then spin transistor with gain 100, and for that 100% or nearly 100% spin polarized material, room temperature magnetic semiconductor, instant boot up computer. I'll describe a little bit. Magnetic logic, spin qubits. So this is important for the quantum science and technology, and I will try to describe a little bit towards the end. Hierarchically assembled media, computer from test tube, and so on, and also nano biomagnetic sensors. Okay, and this was the first magnetic device, which is nothing but a compass. You have all seen it, used it, and to the most modern technology like magnetic hard disk, read-write technology, and very important things like induction motor, magnetic tracker, and so on. There are listless applications of magnetism, and I'm not going into all of them. So what I would try to motivate you in this talk is that, is all spin-based computer possible? Okay, so in that case, you would not depend on the two different material like semiconductor for the processor and the magnetic material for the storage and memory devices and so on. Okay, so you can see this is the architecture of a von Neumann von Neumann computer. So here you have a central processing unit which consists of control unit and arithmetic logic unit, and then you have input device, output devices, external storage, and memory, and so on. Okay, so if you can make so all of these, the input, output device, external storage, memory, you can see they can all be made of magnetic material, and you have already in the market the magnetic read-write sort of recording media. You have magnetoresistive random access memory or MRAM and so on. So if this can be made magnetic, then you need spin logic, spin wave communication, signal processing, and all these things for these to be viable. So and also the power can be given by something called spin torque nano oscillator. I will describe a little bit. So our goal is to devise new technology where we can actually do all this CPU business using spin. So let me just recapitulate how magnetic recording works, although you all use it. So you have a recording medium which is made of a magnetic material, and it has a magnetic moment or spins in it. What you do, and it has a tiny sort of electromagnet with a very pointed and small magnetic field, which actually can sort of align the magnetization in a certain direction to define the bits. So this is the way the bits are magnetized, and then the orientation of this. So basically the binary numbers 0 and 1 are stored in when the orientation are head to head or head to tail. You call them 0 or 1 magnetic state. And you can see the stray magnetic field when they are head to head or head to tail will be different, and depending on the direction and strength of the stray magnetic field, this sort of sensor, which is also known as the GMR sensor or the giant magnetoresistive sensor. So what is a giant magnetoresistance? It is when a material in presence of a magnetic field changes its magnetoresistance, its resistance or the conductance. Okay, so in presence of a magnetic field mean here that the stray magnetic field can change the resistance of the this material, and you can read it by sending a current through it, and as a result you can actually read the orientation of these bits, and then you can read the way they are written, like 0 1 1 1 0 0, something like that, and you can read an information that is encoded by this sort of magnetic bits. So with time, the this is called the longitudinal media because it is here. It is written in the longitudinal direction of magnetization. It has becoming obsolete, So new technology like perpendicular media or even patterned magnetic media, where instead of a continuous magnetic material, you have separate island, which are bits like separate bits whose magnetization will determine whether it is 0 or 1, has been introduced. And sort of we are going towards reduced bit size. And also another important thing is that the faster magnetic switching, because in order to read or write them, you need to switch the magnetization as fast as possible. Only then you can read or write them in gigahertz to high gigahertz regime, which is now in the very slow state. So next is the magnetoresistive random access memory, which is the memory device, which is also based on a tri-layer system. So I didn't tell you that here you have a tri-layer system. So here one magnetization of one layer. So these are two magnetic layers which is sandwiched. Uh, uh, and a non-magnetic layer is sandwiched between these two magnetic layers. So magnetization of one of these magnetic layer, let's say this one, is fixed along a certain direction, which is known as the reference direction. And the magnetization of the other layer is free to rotate. So as a result, in presence of this magnetic field or the stray field from the bits, they will rotate in a certain direction, and they can, in certain circumstances, be parallel or anti-parallel. So when they are parallel, their resistance level is very low. When they're anti-parallel, their resistance level is very high due to the spin-dependent scattering at the interface. Okay, so so this is known as the giant magnetoresistance. So you can go from a low resistive state to a high resistive state and come back to the low resistive state. So the same principle is applied here. Here also you have a reference layer and a free layer. You can see here. But in this case, instead of a magnetic field or GMR sensor, you read or write it by sending current. So you have a crosswire architecture like that. So you can see that these are crosswire architecture, and at the sort of junction, you place one such bit, which is the known as a tunnel magnetoresistance, or also a spin valve. Okay, so so you can just do the same by sending current. You can sort of write the direction of magnetization, and by sending a small current, by using that magnetic field, you can read the sort of the resistance of this sensor tunnel bit, and you can actually understand what is the data encoded here. Okay, the good thing about MRAM is that it's non-volatile, because even if you switch off the power, the magnetization will retain its direction. So it is non-volatile. Whereas in the charge-based technology, it is volatile, because as soon as you switch off the power, the sort of the all the data stored are gone. And it can potentially combine the density of DRAM or dynamic RAM and the speed of SRAM and non-volatility of a flash memory. And it can also work in various very harsh conditions and so on. Problem is that if you reduce the size of these bits or the tunnel bits, anisotropy of this magnetic anisotropy of this becomes very, very high, and then these currents will not be good enough to read or write it, because you require more magnetic field to actually, and then this magnetic field is produced by so by Biot-Savart law, by sending the current through this or the Oersted field created by sending the current through these wires, and that Oersted field is not large enough to switch the bits. So that is why it was difficult at some point to sort of reduce the bit size and increase the storage density. Okay, so if you reduce the size, the density will be higher. So it was difficult, and now people are exploring different technology, which is known as the spin torque technology. You will be hearing STT MRAM or SOT MRAM in the market, and I will describe a little bit of those in my talk. Then you have logic devices. So you know what is a logic gate or something. So you have sort of AND, OR, NOT, XOR, and so many gate, and even the universal logic gate, majority gate, and so on. So these can all be sort of made by using a magnetic material. Okay, so we give you an example. So let's say you take a notched nanowire, magnetic nanowire like that, and then the magnetization of this can be like that. So there can be a domain wall trapped in this direction. So you can see there is a wall and two different magnetization directions, means two different domains are facing each other. So this is a sort of 180-degree domain wall, and on this side there is no domain wall. It is kind of uniform, magnetized. So now you apply a rotating magnetic field, and that will push this domain wall through this notched wire and bring it to here after certain, sort of rotation. And you can see, like, after it rotates by 180-degree, the domain wall actually moves from here to here. So if presence of domain wall is called 1 and absence of domain wall is called 0, so here you have 1 to 0 state, and here you have a 0 to 1 state, because there is no domain wall, here there is a domain wall. So you can easily achieve this NOT gate like 0 1 1 0 logic, and you can do the other logic gates as well. And there is no logical mistakes for
Sir,
every. Yes.
Sir, can you explain this, how these spins are changing from each domain wall? Like, can you repeat it again, please?
Yeah, it is nothing but as the magnetic field is rotating, so you can see that it will exert a torque on this. Okay, and that torque will slowly rotate the magnetization direction. Okay, and as a result, this domain wall will be moved, and they will be pushed from here to here. If you follow that, you can see that it is, when it is here, the magnetization is trying to align with this direction. When it is here, it is more towards that, and then the domain wall is pushed from here to here. And as it is in this direction, now this part is now aligned with this magnetization direction, and this part is, so the domain is now on this direction, and here it is uniformly magnetized. So, I mean, it is not very important to understand this part. It requires more understanding of the domain and its interaction with the magnetic field. I am just giving you an example that the domains can be rotated, uh, can be pushed, and a domain wall logic can be, sort of built based upon that. Similarly, domains can be used for storing information, because if you consider each domain as a bit, you can send current and move the domain in such architecture, which is like that. So these are called racetrack memory, and you can see that they are like a three-dimensional architecture. They can be arranged like that. And Professor Stuart Parkin, that time in IBM, now in Max Planck Institute, he actually discovered it, and it has gone a long way since then. But the good thing is that this is a 3D architecture, so from a planar architecture, it is a, another degree of freedom, or another dimension will be added, and you will be able to, store more information. And then we come to the, another example. So these are all examples. I've not come to the basics yet. I'm just trying to show you that these are the devices that works, and then how they work and all this will be understood after I go through all the basics, the theory and all this. Okay. So this is called spin torque nano oscillator, and that can act as a microwave source. How it works is like that. You have two magnetic layers separated by a non-magnetic layer. And if you send current through a ferromagnet, this current becomes spin polarized. Okay. So what happens is that most of the electrons are, polarized along a certain spin as opposed to the other spin. Let's say it is up spin. So you'll find more electron will up spin with less electron with down spin. So there will be a net up spin. So this is called spin polarized. So that spin polarized electron will be able to cross this or tunnel through this barrier and be entering or injected into this second ferromagnetic layer. And now it has a magnetization, so it will exert a torque on the second ferromagnetic layer. So if it exerts a torque, and I will show you later how it works, it will create a spin wave in this the second magnetic layer. So that spin wave will emit some energy, okay, and that energy is in the gigahertz regime, because spin waves energy is in the gigahertz regime. But the point is, an individual oscillator has only 10 nanowatt of power. Okay, so if you have only one oscillator, but if you can synchronize them, then the energy goes as the power, as a square of the number of oscillators. So here, the first time it was shown that two oscillator can be mutually synchronized in this Nature paper, and then the power will be 2 to the power 2, that is 4 times that of the single layer, single oscillator. So similarly, if you can synchronize n number of oscillator, then the overall power will be n square. So that will be a huge increase. So if you can, sort of 10 nano oscillators can be synchronized, you can go from 10 nanowatt to a microwatt, and that will be good enough for sort of many purpose, because this is in the gigahertz frequency. So finding on-chip gigahertz power source is not very easy. You can actually use them for as a clock or reference oscillator for directional microwave transmitter, receiver in cell phone, radar system, computer chips, and so on. So this is also a new field of research which is gaining a lot of interest. And then the other thing is called magnonics, or based on spin waves. So I describe what is a spin, but I haven't really described yet what is a spin precession. But you know that every spin can undergo a Larmor precession in presence of a magnetic field. So, and that precession is like that. So it precesses in a cone basically due to the torque from this magnetic field. So let's consider that a one-dimensional chain of spin is lying in the ground state, and you you perturb one of the spin, and that start to press. Now these spins are all coupled by the exchange interaction. I will describe what is exchange interaction, what is precession, everything. For now, just understand that, assume those, okay, if you do not know about it. So because there is an exchange coupled system, so because this spin is precessing, that will perturb the next spin, and that will also precess, but at a certain phase lag. So this also will precess, but with another phase lag, so on. So what will happen in all the spin will be precessing, but in a periodic phase lag. And if you can see from the top, actually, the positions of the spins will be like that, and that will look like a wave, basically. So although no physical motion of the particles or the electrons are happening, but a wave is propagating through the media, and that is a collective excitation of the spin, which is known as the spin wave. And it can be quantized, and the quanta of spin wave is known as the magnon. And interestingly, the magnon are boson because they are spin one particle. Although electrons themselves are fermion, spin half particle, magnons are bosons. And in 2 and 3 dimension, you can have such kind of magnon or spin wave, and they can be used for various technologies that I will describe a little.
So we have a question from audience.
Yes.
So Manjusri is asking that the spin wave are in gigahertz frequency range, right? So in general, it is only in gigahertz ranges, or do we have any other ranges for the spin wave?
No, it can go from gigahertz to even terahertz range. Okay. So so for certain material like antiferromagnet, it can go to few terahertz frequency range. For ferromagnet, it is usually in gigahertz to hundreds of gigahertz. Okay, and it depends on many factors like applied magnetic field, magnetic anisotropy, internal field, and so on. Okay, so yeah, so so this opens a new field called magnonics, where instead of electron, you use actually the magnon, and instead of a normal crystal, you use an artificial crystal. I will show how it looks like. Artificial crystal made of some magnetic material, periodic arrangement of magnetic material, which is known as the magnonic crystal. So, and we study the propagation of spin wave through this periodically modulated magnetic media, and that opens up the magnetic band structure and band gap in gigahertz to sub-terahertz or even in terahertz frequency range. So it can give you a very fast on-chip data transfer, logic, and various other devices. So far, many prototypes of these magnetic devices have been shown, like holographic memory, spin current control, 3-terminal magnon transistor, and so on. Sorry, I just wanted to replace it with another one. I didn't do that. Okay, there are logic and other things. Okay, so like I said, these are artificial crystal or metamaterial. These are based upon spin wave quasi-particle or magnon. And you can see this is a one-dimensional periodicity. Here you have a two-dimensional periodicity. Here you have three-dimensional periodicity. So these are 1D, 2D, and 3D magnetic crystal. And it can go from a sort of various bands of microwave to terahertz frequency range. As you can see, all the microwave band, millimeter band, sub-millimeter band can be covered by these magnons. So a huge scope opens up because microwave and terahertz frequency range are not easily accessible, particularly on chip. Okay, so it opens up a new sort of field, and these are sort of actually proper devices that we made by using lithography, electron beam lithography. These are like patterned holes, two-dimensional arrays of hole in a magnetic film. These are patterned nanomagnets, and you can see they have different. This is a triangular lattice. This is a sort of hexagonal lattice, and so on. Okay, and they can open up, sort of magnetic band gap like that. So here you can see that in the Brillouin zone there is a gap. This is the magnetic band gap. Here, in between the two 0 and Brillouin zone, you have a magnetic band gap. So you can tune it, you can play with it, and you can make different kinds of properties and material that is not normally possible. So there can also be biomedical applications of nanomagnets, like I said. That is because if you have a magnetic field gradient like del B, and if you put a magnetic particle with moment m, then it will experience a force m dot del B, right? And as a result, if it experiences a force, it will move. This force can also be explained like Vx del half B dot H, where chi is the susceptibility of the material, and this is proportional to the gradient of the magnetostatic field energy density. And it will act along the direction of the steepest ascent of the energy density. So what you can do is you can actually do targeted drug delivery. So you can attach a drug to a nanomagnet, and then you inject it into the patient, and then by applying a magnetic field by some magnet from outside the body of the patient, you create this magnetic field gradient, and you can move it to a specific location by this external magnetic field, and then you release the drug. Okay, if you withdraw the magnetic field, the sort of drug will be released at that particular point. So it limits the drug to the specific location of the body, and so only the malignant tissues of the cells will be affected by the drug, not the healthy tissues, and it avoid the adverse side effects, lower the required dose. The other thing is called the hypothermal treatment, or the hypothermia. This works on the principle that the cancer cells, they are most susceptible at a temperature of greater than 42 degrees centigrade than the normal cell. Okay, so what you can do is, again, you put a dose of drug with magnetic nanoparticles, and you inject it, and sort of locate it, move it, and sort of release it at a particular region of the malignant tissue, and then you apply an external alternating magnetic field, or AC magnetic field, and change the frequency of that magnetic field. And this magnetic nanoparticle has a natural magnetic resonance frequency. So when the external AC magnetic field has match the resonance frequency of this the magnetic nanoparticle, there will be resonance, and at resonance it will absorb energy from outside, and after absorbing energy, it will be released in terms of heat, and then the region of that particular cell of the body will be heated up, and this cancer cell will now be treated at sort of by this dose of drug by the infected cells, whereas it will not sort of do anything to the surrounding tissues. So there are numerous applications of that. Before
Sir?
we yes.
So what will be the strength of these external magnetic fields that we use? And
It depends. It depends very much, but it can be of the order of a Tesla or something like that. Okay, so which is like 10 to the power 4 Gauss.
okay.
Okay, but it can be more, it can be less. It depends on the many properties of the magnetic particle, the magnetization, anisotropy, and various properties. So after I go through all these basic theories, I think it will be clear to you. So that is why I wanted to start. I first wanted to give you some example, so that I'm getting questions. That mean you are now interested to know more about the basics, right? So my job is partly successful. So now I will go into the basics. So I will start from the electromagnetism. Like everybody knows what is electromagnetic theory. You know what is Oersted field. You send a current through a conducting wire, so you create a magnetic field like that, and the direction of current is determined like that by this thumb rule. And then you know that this Ampere's law, you know the Gauss's law, you know the Faraday's law, and the Lorentz force, and so on. And you also know this gentleman James Clerk Maxwell in 1861-62. He actually sort of combined all these laws and also kind of fixed the Ampere's law by including something called a displacement current, and then that was his contribution. And then he put up so Maxwell's equations, and in every interview everywhere, the student are asked this, what is Maxwell's equations and all this, right? So it's very important in sort of classical electromagnetic theory, as well as sort of other things. So and then there is something called Lorentz force. So if you have a charged particle in electric and magnetic field, so it will experience a drift due to the electric field, and it will also have something like a torque due to this magnetic field. So it will move in a certain direction, and that can be given by this Fleming's right-hand rule and so on, where this is the direction of the charge, positive charge movement. This is the direction of the magnetic field, and this way the force will be exerted on the the charge. So we know that, and then we will come to the classification of magnetic material. Like I was saying, there are different kind of magnetic properties or material. One is, of course, the diamagnetism, which was discovered way back in 1778, and it is shown in bismuth and antimony for the first time, and now you can see it in various other material, including glass and so on. So it actually repels all the magnetic field. So if you put a diamagnetic material inside a magnetic field, it repels the magnetic field outside the material, and that means it has a negative susceptibility. So we call this M equals to chi h, where M is the magnetization, H is the magnetic field, and chi is the susceptibility. And here chi is less than 0. You have a negative susceptibility like that. Okay, and chi can be determined by the Langevin equations, formalism like that, and so on. So in 1905, Langevin actually proposed the theory of diamagnetism and also the paramagnetism. So paramagnetism is another kind of magnetic property which was discovered after diamagnetism. And here the spin angular momentum plays a role. Okay, spin moment. So you need to have atomic magnetic moment due to the unpaired electrons at the outer shell. So that will give you some magnetic moment. but you don't get any net magnetization at the zero magnetic field. So at zero magnetic field above Curie temperature, you have a there is no Curie temperature here. It's normal paramagnet. In ferromagnet above Curie temperature, it is a paramagnet. So under normal circumstances, thermal energy and no magnetic field, the spins are all misoriented. They will be randomly oriented like that, and the susceptibility is given by this law, chi equals to Cp over T. So as you can see that if T is very large, then this becomes very close to zero, and when T is very small, this becomes close to infinity. So you have 1 over T like behavior. Okay. And then this is ferromagnetism, which actually has a Curie temperature. So above Curie temperature, the ferromagnets behave like a paramagnet. So you have similar behavior like that, the susceptibility. But below Curie temperature, it is has a different kind of behavior. It shows a curved behavior, and that is also temperature dependent. And the paramagnet also has the M versus H, which is positive. Slope is positive. Slope is very small. So here chi is greater than 0, but chi is very small. Whereas in ferromagnet, not only the chi is large, but you also see a hysteresis. So you can see that the loop is open. For a paramagnet, it will be just like a line, right? For a ferromagnet, you see there is a open, like a loop, like the loop is closed, but there is a area under the loop. Okay. So only at a very high field, the loop closes. So this is called the saturation field, when the magnetization becomes saturated. So all the moments are aligned in a certain direction. And if you reduce the magnetic field, they become slightly misoriented, but at the zero field, it doesn't become zero. The magnetization doesn't become zero. So this is called the retentivity or the remanent magnetization. So you have a finite amount of magnetization even at zero field. So in order to reverse it, you have to give a negative magnetic field, which is known as the coercive field. So there it starts to reverse, and at this negative saturation field, it becomes completely reversed. So if you go back, again, you have a remanence, and you have to apply a positive coercive field, and then again it saturates. So this is the hysteresis loop, and area under the curve is basically the energy you store, for this by this applied magnetic field into the medium. And also there is something called antiferromagnetism, where the moments are anti-parallel and equal. So there is no net magnetic moment. Here the exchange integral is less than 0. Here the exchange integral, I will show what is exchange integral is greater than 0. So here you have a nil temperature, and below nil temperature, it actually goes down like that. It also follows a sort of a Curie law, Curie-wise law, but here you have a, instead of a Curie temperature, you have a nil temperature. Okay, so the ferromagnetism was first described by Wise by considering something called a molecular field, or the Wise field, which is given by Hm equals to H plus gamma m. But later it was found that Wise was correct, but he did not give any explanation or any microscopic mechanism of this field, molecular field. Later, Heisenberg actually explained this molecular field, and it comes from the quantum mechanical exchange interaction. And here you will see how the sort of quantum properties or quantum principles will be coming to play. So here, this is Heisenberg's exchange interaction. So let's say you have a 2-electron system, like a hydrogen atom, and you know what is a Hitler-London model, or you may know for hydrogen molecule. So the wave function will have a spatial part and a spin part, and they are separated by, let's say, a distance RAB. So this is 1 and 2. So psi R1 S1, this is psi R2 S2. Now there's a law called Pauli's exclusion principle, which shows that no two quantum particle or indistinguishable sort of quantum particle can occupy the same quantum state. Okay, So electrons or some other fermion, they follow the Pauli's exclusion principle. So two electron with the same spin state cannot be, sort of in principle be occupying the same quantum state. So the basically the consequence of this Pauli's exclusion principle is that the combined wave function of these two electrons must be antisymmetric. Okay. So let's say what is antisymmetric. So if it is antisymmetric, psi antisymmetric means that if any of these coordinates are exchanged, it becomes negative of the sort of the wave function. So in order to do that, either the space part is symmetric, phi symmetric R1 R2, and the spin part is antisymmetric, chi antisymmetric S1 S2, or the other way around, the space part is antisymmetric and the spin part is symmetric. Okay, so you can do either of them. So here we see that here sort of space part is symmetric. So this is called psi S. So here A phi A R1 phi B R2 plus phi A R2 phi B R1, whereas the spin part is antisymmetric. So is a minus sign here. So as a result, that means that the spins are anti-parallel, and then the net spin will be 0. And this is called the singlet state. So there is only one state here. Whereas an ES, the energy is given by A squared K12 plus J12. K12 is the Coulomb exchange, and J12 is the Heisenberg exchange. Okay. And then there can be space part antisymmetric and the spin part symmetric. And here you can see instead you have a plus sign, or just the spins of the two particles combined. So you can have three different spin state. So S equals to 1 because spins are parallel. So you have 2s plus 1, that is 3 states. So it is called a triplet. So these are the 3 states, and this is the antisymmetric space part. So the energy of the triplet is basically B squared K12 minus J12. So this J12 is known as the exchange integral, and which is given by basically phi A star R1, phi B star R2, and H12 is the Hamiltonian, and then phi A R2, phi B R1, and d tau 1, d tau 2. So this is the exchange integral, and for the parallel alignment of spin, this J12 must be positive. Okay, whereas if J12 is negative, then it is anti-parallel. Okay, so now you can understand that for ferromagnet, you have a parallel alignment and J12 is positive, the exchange is positive, whereas in antiferromagnet, spins are anti-parallel, so this is negative.
So we have a question from audience, Srinath.
Yes.
So
yes.
what is this exchange integral is? Like a physical meaning or something like that?
Oh, the physical meaning is that if you sort of exchange the coordinate system of these two integral of these two wave function, basically. Okay, so then and take the integral of that. That is your exchange integral. So it is basically exchanging the coordinate, whether the space or spin. So just exchanging the. Basically, you are exchanging the two. You are keeping the same space, but particles are exchanged from one state to another.
So is it like physically, can we think it as energy? Like how much energy we put it
Yeah,
to exchange?
that is the energy. This is the energy that is required for doing that. Yes, but that is when you are exchanging the position of the particles. In this case, you have two different particles. So if you put this one here and this one here, how much energy will be cost? How much will be the energy cost? That is the exchange integral. Okay. So and if you make them also the spin, for spin you have to not only exchange the position, but also you have to flip their spin sort of direction from up to down and down to up. Okay. So for parallel alignment, J12 is positive, and for anti-parallel alignment, J12 is negative. And if the interatomic spacing RAB is large compared to the radii of the orbital, then this condition is fulfilled for D and F wave function for certain iron group elements or rare earth metals like nickel, cobalt, iron, or gadolinium, terbium, and so on. Okay, so this is called direct exchange, and here you can also have Heisenberg, the indirect exchange. For example, this is called super exchange or double exchange. So here, instead of just directly exchanging the spin or of the two electron, you can also sort of do it through another ion here. Let's say oxygen ion. So here manganese 3 and manganese 4 have a different spin system, as you can see. Here you have one spin here in the excited state. Here you have no spin, so you can do this just through this oxygen ion. So oxygen takes this spin and then transfer it to this manganese 4, okay, ion, and this is mediated by oxygen, and that is why it is called super exchange. You can also have indirect exchange, where this exchange integration or exchange integral is done through the electrons in the system, or something called RKKY exchange, and so on. So, I mean, there are a lot of theory behind it. It's very difficult to just, qualitatively, explain it in one lecture. It requires many lectures for that. But just in a nutshell, that for two atoms, if you take Si and Sj are the two spins, okay, then the exchange energy or the Hamiltonian is nothing but minus 2 Jij Si dot Sj. Okay, and you can see here that if the two spins are parallel, then Si dot Sj is sort of positive, and then the overall energy will be negative if Jij is positive. And if the overall energy is negative, is a more stable state. And so as a result, if you want them to be ferromagnetic, Jij has to be positive. On the other hand, if they are antiparallel, then Si dot Sj will be negative, and then you will have, Jij has to be sort of negative. So these two negative cancel out. So you'll have net energy, which is negative, which will give you the stable or equilibrium state. So so this is for two atom, and for a crystal you can have like summation over Ij. So here Jij can be taken out of the sort of summation, and then this is Si dot Sj summation over Ij for a crystal periodic arrangement of atoms. Okay, so this is one thing. The other thing is the Stoner criterion for ferromagnetism. This is also very important, because in a ferromagnet you have a spin split band structure. So the energy versus the density of state is like that. So here on this side you have spin up electron. This is the Fermi level, and this is the spin down electron. Now this happens if the relative gain in exchange interaction, that is, the interaction of electron via the Pauli exclusion principle, is larger than the loss in kinetic energy. So you have to, sort of have competition between two energy. One is the exchange interaction energy, the other is the kinetic energy. So for the spin up electron, epsilon up k is nothing but epsilon k minus, because it is shifted downwards, minus the exchange energy, which is I times n up minus n down. That is the number of electron with with spin up, number of electron with spin down, divided by the total number of electrons. And here I is called the Stoner parameter. I'll come to that. So here you can see there is a downward shift from this equilibrium energy, the reference energy, and here for the down spin you have epsilon k plus I times n up minus n down over n. Okay, so that is why it shifted upward, and this n up minus n down by n is called the spin polarization. So the basically the net up spin or down spin that you have in this system divided by n. So a system with 100% spin polarization means you have basically all spin that are up and no spin that is down, basically. Okay, So that is very difficult to achieve, but it's possible to achieve in certain material. But anyway, you come to the Stoner criterion. So magnetic moment is given by infinite, basically an integration over minus infinity to EF, and then the density of difference between the density of state of the up and down electron and dE, and the Stoner criterion for ferromagnetism is given by that. So here I times the density of state at Fermi level should be greater than 1. Now it turns out that the density of state is 1 over W, where W is the bandwidth, which is also given by 1 over T, where T is the hopping parameter, and Z, square root of Z, Z is the atomic number, okay, on the nuclear charge. So in case of iron transition metal series, for example, iron, nickel, cobalt, and so on, or even the rare earth magnets, this hopping parameter T is very, very small. As a result, dEF is quite large, and the multiplication of I times dF, I is the Stoner parameter, which is the ratio of exchange energies and magnetic moment. Okay, so the Stoner parameter is determined by a magnetic material, and if the density of state is relatively large, then there is a high possibility that you will fulfill this criteria and you will have a ferromagnet, and that is why this iron transition metal series are ferromagnet. So I'll very quickly go to the magnetic energies in the system. So total magnetic free energy is given by various energies. Let's say the Zeeman energy, the dipolar energy, exchange energy, and anisotropy energy. I already explained what is exchange energy. Dipolar energy is that the simple dipole-dipole interaction that you have already studied in the sort of your electromagnetic theory, and it can actually potentially be given by basically, and then there is a Zeeman energy. This is nothing but m dot h and an integration over the whole volume, that is a Zeeman energy. Then the magnetostatic self energy or the demagnetizing energy is given by minus half again m dot h d cube r, and the potential energy associated with the stray field here hd, that is the stray field, can be found out from here. You can see that I'm not going into the detail of that, but just you can see that here rho v is the volume magnetic charge and sigma s is the surface magnetic charge. If you can find out the volume and surface magnetic charge, you can find out the total energy from this expression, and you can calculate the energy just by from this expression for ud. So this is the potential energy. This is the magnetostatic self energy, and the exchange energy. I have shown you that it is basically Si dot Sj and then Jij. But for a continuum medium, I can also write it as continuously varying magnetization. So del m square dqr and summation over the volume, which is also given by A is given by 2j E times S square over A. Where A is the lattice constant, J is the exchange sort of parameter, and S is the spin. And magnetic anisotropy, that is related with the spin orbit coupling or the crystal field interaction of the electrons. And for different symmetry like cubic system, hexagonal system, you have certain different expression for that. So you have certain axis which is known as the easy axis, and certain axis which is known as the hard axis, along which magnetizations are easier to orient and hard to orient. Okay, and that are often related to the crystallographic axis of the material. Okay, so now you know what is different magnetic energies, so you can understand that there will be competition between those energies, because some of the energy, for example, dipolar energies, are long range interaction, but they are trying to make the systems anti-parallel. So dipolar energy prefer the sort of minimum energy state when the spins are anti-parallel, whereas the exchange energy prefers the minimum energy state when the spins are parallel. So there is a obvious sort of competition. again there is a Zeeman energy for the external magnetic field that will try to align all the spin along the magnetic field direction. Okay, and then there is also anisotropy energy that will try to align the spins along certain crystallographic axis. So you can see so many, competition of energies, particularly the long range dipolar energy and the short range exchange energy. So what happens is that the exchange energy is very strong, but it is short range. So in the short range or in the short length scale, the exchange energy wins. So it makes the spins parallel in a shorter length scale, whereas over a long length scale, the dipolar energy wins, and as a result, you'll have sort of anti-parallel kind of alignment in the long range, and that gives rise to something called domain. Okay, so domain theory was first developed by Pierre Ernest Wise in 1906. So who actually also give the Wise molecular field theory. And like I say, it is between due to the competition between dipolar and exchange interaction. So you can see that if you have a parallel magnetic alignment, so here there is a large exchange energy cost.
So we have a question from the audience.
Yes.
So the anisotropy shown in the previous slide, is it that uniaxial one or?
Oh, there can be various. It can be uniaxial, it can be cubic, it can be even unidirectional. It depends on sort of material and the system. Okay, and it can also be induced in the system. Okay, and there can be sort of biquadratic and different kind of anisotropy. So I mean, I'm not coming into the detail of that at the moment. I'm just giving a flavor of that you can have anisotropy in the system. So now you see that here you have parallel alignment of spin, but that costs a large exchange energy. So if you make a domain like that, then you somewhat reduce the exchange energy cost because now dipolar energy is also playing a role. And the best possibility would be a closure domain structure like that. So you can see that here the magnetization is along that direction, like that, here like that. So that will give like that the total flux of energy remain within the system. For this case, what will happen is that here the spins are pointing in this direction, here the spins are pointing in this direction. So there will be stray field which will come out of the system and follow the field lines, and then will be ended here. So a lot of energy will be lost outside the system. So you will lose a lot of energy outside the system. Okay, here it will be from here to here. The stray field will go from here to here and from here to here. So still some loss, less loss, but some loss. Here there will be almost no loss because it actually creates a flux closure within the system. Okay, so this is the sort of holy grail of forming the domains, and there can be different types of domain. This is a multi-domain structure. This is called a vortex domain where you can have circular magnetization with a sort of core which is coming out. There is a ring vortex like that, and you can have quasi single domain system where you can have this non-uniform like magnetization. So most of the part is uniformly magnetized, but at the edges you have demagnetized region. So this is called C state because it looks like a C. This is called S state because it looks like S. Here you call it a flower state. This is a leaf state, and so on. So there are different kind of quasi single domain state in a system. And a little bit more that you can have an interface which is separating the domain. So there will be a domain wall, and the domain wall is sometimes.
So we have a question from the audience.
Okay.
How is vortex domain is achieved?
I mean, you don't need to know at this moment. Okay, this is all due to the competition between the energy. Okay, so I can give you, sort of an exercise for a certain material, and you can calculate or sort of simulate yourself that how vortex is achieved. So these are all like domains to minimize the overall energy of the system. So this is called the domain wall, and you can see from this domain to this one, I've just expanded the domain wall. Basically, it doesn't just, so here you see that it looks like there is a sudden change in the spin from up to down, but it is not like that. If you zoom on this wall, you will see that there is a range of or a region of space where the spin slowly goes from up to down like that. So it bends and goes like that. Okay. So this is called a domain wall. This is a nil wall, and here you can see it goes like that. It goes into the plane of the system and come out again, and then it's like that. So this is called a block wall. And there can also be 360-degree wall, and wall loop. This is a linear 360-degree wall, and so on and so forth. Okay. So the good thing about the domain is that you can actually have some of the question you can save it. I can answer after the talk is over.
Okay, sir. Okay.
So because it will stop my disturb the flow of the talk actually. So the domain wall assisted magnetization reversal is like that. So if you have a system which is magnetized along, let's say, up direction, which is shown by red, and then you apply a magnetic field in the opposite direction. So what happens is that some domain are formed, and then the domain wall is pushed slowly, and it is pushed along that direction, and you can see that, and then the blue domain arises, and slowly it is pushed, and finally completely blue means it is, let's say, in the downward direction. So that is how you can actually get a complete reversal of magnetization through domain wall movement. Now you will be so I have now talked about domain wall. I have not talked about the other thing, and also I have talked about the exchange interaction. Intermediate I have not talked about. So you can see the time scale of these fundamental time scale of spin dynamics. The exchange interaction, it actually like occurs in the femtosecond time scale, 1 femtosecond. That is 10 to the power minus 15 second. Whereas the domain wall motion occurs in the microsecond to hundreds of nanosecond time scale. That means 10 to the minus 6 to 10 to the minus 9 second. So in between there are various other sort of phenomena, something called spin orbit coupling, which is in this picosecond time scale, and then you can have precession. I talked about Larmor precession, but you have magnetization precession as well, and damping of that, and so on. And then vortex code switching, spin wave, and all these things occur in this time scale. Okay, so magnetization reversal mechanism I was describing, but there is a and also I showed you a hysteresis loop. So that is the trace that how magnetization reverses from up state to down state, or sort of right hand side to left hand side, and so on. So hysteresis loop just show you that there is a reversal, and what are the parameters like saturation field, coercive field, remanent magnetization, and so on. But it does not give you the mechanism of how it occurred. And for that, you need to do something called a micromagnetic theory. And you can do this by micromagnetic free energy calculation. So here you can see the total energy is given by this is the exchange energy. This is the basically the dipolar energy. This is the Zeeman energy. So this is the dipolar energy. This is the anisotropy energy, and sort of this is the Zeeman energy. Okay. So now, if you actually solve it, the phenomenological expression for the coercive field that you can find out is given by alpha k to k1 over mu 0 ms minus d effective times ms minus delta h. So this is what you get. Alpha k is called a Kronmuller parameters, and so on. So you can actually find a formula by which you can sort of, if you know what is the anisotropy, what is the magnetization, and so on, you can calculate it. but you will still not be able to see how it occurred. But using the micromagnetic theory of simulation, you can actually get how the magnetization reverses, and there are different types of reversal. This is known as the coherent rotation. So what happens is that you can see all the spins are in phase. They're all directing in the same direction. So what happens that you have, it's a double potential well-like behavior, and you have a barrier between the double well. Okay. And one well is spin up, the other well is spin down. So you have the spin has to cross that barrier from the up to down. Okay. So overall energy required is that you have to supply the full energy barrier, and then all the spin will go from up to down. So this is called the coherent rotation. All the spins will in unison together, they will rotate from up to down. Okay. So this is called the coherent rotation or coherent reversal. But they can also form some other sort of mode, which is, let's say, incoherent rotation or curling mode. So they curl like that. Curling mode in a cylinder, you can see how they curl into a cylinder. There can be buckling mode, so you can see that there are regions when they are sort of pointing up, and then they are like that. So it is called a buckling mode, and this is called a fanning mode, and so on. Okay. So there are different types of reversal mode or mechanism. So now I will come to the precession of magnetization. So I have shown you or told you that if you have a magnetization which is in a magnetic field, there is a torque, and due to that torque, it actually precesses in this cone around this magnetization. So this is dm dt is or the rate of change of magnetization with time is given by this precessional torque. But it cannot go on forever because energy has to relax because the spins are coupled with lattice and other sort of degrees of freedom. So they finally come down and meet the equilibrium again. So here there is a damping which is along that direction. So finally the M will be aligned with H. So it will actually go, instead of like infinite precession like that, they will slowly damp and follow such kind of spiral path, and then finally align with the magnetization. Okay. So then it will reach the equilibrium. So this is called the precession of magnetization, and this is governed by something called the Landau-Lipschitz equation or Landau-Lipschitz-Gilbert equation, which is like that. So it is dm dt, rate of change of magnetization, which is given by minus gamma. Gamma is called the gyromagnetic ratio, okay, or magnetomechanical ratio. And then M cross H effective. M is the magnetization, H effective is the effective magnetic field. And then there is a damping term, alpha over ms, M cross dm dt, which is a force, central force going like that. But one can actually, this is a phenomenological equation, but one can actually derive it from a quantum mechanical principle. How do you do that? I'll just very quickly go through it. If you do not understand, I mean, I can share the slides, and you can go through it carefully and you can get it. So the commutation of spin observable S with the Hamiltonian, it can be given like that. So it is basically SH, and that is given by the time evolution of the spin. So basically IH cut ddt of the expectation value of S is given by the commutator relation with S with H. Okay. And the interaction of S with the magnetic field vector is given by like G mu v over H cut S dot B, and this is the spin Hamiltonian. Okay. Like this Hamiltonian. And we know that the commutation relation for the spin operator is given by SI is given by IH cut epsilon ijk sk. Okay, this is the standard commutation relation. So if I now take the time derivative of the spin vector, then I can actually show that if I take on this side, so this will become d dt of SI sj, it will become sort of sk. So it is basically something like S cross B. Okay, this can be derived. I can show you how it can be derived, but ddt of S is given by S cross B, and then G mu V over H cut. Okay, so this is from certain derivation by taking the time derivative of the spin vector. And in the macro spin model, the magnetization is given by G mu V over H cut S, the expectation value of S. So here you can see that you can actually put this in terms of M, so and also this in terms of M. So basically then this will become dm dt equals to G mu V over H cut M cross H, basically M cross B or M cross A. And now I am not writing H as this Hamiltonian, but a magnetic field, okay, because we know that B equals to mu 0 H, so we can write that. So this is the G mu V over H cut is basically the magnetomechanical ratio or the gyromagnetic ratio is minus gamma M cross H. So this is the precessional torque, and then there is a relaxation term which was introduced by Landau-Lifshitz, and later on Gilbert gave this term. So this is the basically the Landau-Lifshitz-Gilbert torque equation, and this governs the precession of magnetization like that. And you can understand that if you have not just a single spin but a number of spin, I showed you earlier like how a chain of spin behaves, or a two-dimensional or three-dimensional behave, because this H effective has both a space dependent and time dependent property. So then it can actually propagate through the medium, so like a spin wave, for example, like that. So here you can see the spin waves are propagating along this direction with a wave, and a propagating wave will have a wavelength and a wave vector k equals to 2 pi over lambda. Lambda is the wavelength. So this is for a planar structure, and for a 2D and 3D structure, you can also define kx, ky, kz, and so on. And this is the plane wave solution of this Landau-Lifshitz-Gilbert equation, which is known as the spin wave, basically. And this is the uniform eigenmode of the system when we consider that all the spins are precessing in phase. So there is no phase difference between the two, between the nearest neighbor. Okay, so this forms the basis of spin wave. Now, like I said, you have dipolar energy and exchange energy. So the exchange energy will give you a short range spin wave, which is like I showed you before, and the dipolar energy can give you a long range spin wave. Okay, and that is because dipolar energy is asymmetric. It depends on the direction of the magnetization. So as a result, the dipolar energy will have different configuration, whereas the Heisenberg exchange energy is isotropic, because everywhere you go, it is like the same. So there will be again a competition between frequency and wavelength, and you can see that if you have very short wavelength, basically the exchange spin wave will be very large, like that. Frequency will be large, and intensity is also large. Whereas for longer, sort of wavelength, the dipolar energy will be dominant, and sort of in between, they have dipole exchange spin wave. Okay, so this is something like here they basically merge at a longer wavelength, dipolar and exchange, spin wave merge basically, and this is something called sort of the dipolar spin wave, the surface wave, and the volume wave. The surface wave basically propagates through the surface of the material, and the volume wave can penetrate into the bulk of the material. Okay, and this is called magnetostatic surface spin wave, and you can see that this blue color is the magnetization direction, and the blue color is the wave vector direction, and the red color is the field or magnetization direction. So depending on the relative orientation of the magnetization and the wave vector, you can have different kinds of spin wave. So this is surface spin wave, or the magnetostatic surface wave, where both are in the same plane and perpendicular to each other. This is forward volume wave, where sort of the magnetization is along the perpendicular direction, whereas the wave vector is in the plane of the magnetization, and here both are in the plane and along the same direction, and they have different dispersion relation like that. So because of that, you can form different kind of spin wave propagation, and you can actually use them for different devices. And then the fastest dynamics is the ultra-fast demagnetization, like I said. So basically what happens is that if you have a material in the saturated magnetic state, and if you actually apply a laser, and you have a magnetic field which is holding the saturated magnetic state, if you shine a laser on that, so there is a coherent interaction. So basically angular momentum transfer from the photons to the spin, and there's a coherent interaction between the photon charge and spin degree of freedom. Okay, and then the incoherent interaction starts, and they become out of phase with each other, and then you see a ultra-fast demagnetization. So from an ordered state, they become disordered, so they become demagnetized. And after some time, they start to remagnetize again, and they start to precess. So you start to see the precessional magnetization and damping. So this is when you use a femtosecond laser to, sort of excite the magnetization dynamic. So now I come to the experimental technique. So there are different techniques. One is the time domain. So you can, in the time, with the time scale, you can see what is happening. So that is why it is called time domain technique. So you vary time and you see how the magnetization is evolving. And that can be done by using something called time resolved magneto-optical Carr effect, which is optical, electrical, or spin torque excitation, optical detection, and it can have spatial and temporal resolution. You have a frequency domain technique known as a ferromagnetic resonance. You have electrical spin torque excitation, and you have electrical detection, and you have a frequency resolution, and you have a wave vector domain technique known as the Brillouin light scattering spectroscopy. Here, basically excited by thermal energy or electrical or optical energy. You can have again optical detection, but you have a wave vector resolution. So you can do the energy versus wave vector, that is a dispersion relation you can find from here. So magneto-optical Carr effect, some of you may have heard about the Faraday effect, or even done experiment in your classroom. So here, if you shine a laser, polarized laser beam into a magnetic material, its state of polarization rotates after being transmitted or reflected from the material. And that rotation of polarization is a signature of the magnetization of the system. So you can essentially read or detect the magnetization state of the system just by reading the change of polarization that happened after transmission or after reflection from the magnetic material. So this is called the magneto-optical Carr effect when it is reflected from the. So what happens is that, like that, so you have a sort of reflection coefficient in the light, and it actually introduced, and due to a normal reflection from normal metal, if it's reflected, you only have the reflection coefficient. But from a magnetic material, there will be another component which is an orthogonal component in the electric field vector, and that is like that. So that orthogonal component make it from a linearly polarized to an elliptically polarized, because the phase between these two will make it elliptically polarized. Okay, the magnitude and the phase between these two vectors will make it an elliptically polarized light. If they are not equal, they will anyway be elliptical. Okay, and if they are equal and have certain phase, only then they are circularly polarized light. So this small ellipticity or Carr rotation, which is read from here, can be detected by some mean, and that will give rise to the state of magnetization of the material. And here, this is the Carr rotation, and this is the ellipticity. They are related by this expression where K is the sort of absorption coefficient and R is the reflection coefficient. And they have different geometry. You have a longitudinal geometry where the magnetization is longitudinal. You have a transverse geometry when magnetization is in the transverse direction to the plane of incidence, and you have a polar geometry when magnetization is lying in the plane of the incidence, but it is actually perpendicular to the surface of the this magnetic body. So you can have different kinds of behavior. Basically, in transverse polar Kerr effect, you have no change in the polarization, but there is a certain change in the intensity of light when you changes the sign from plus m to minus m, whereas from longitudinal and polar, you have a certain Kerr rotation which you can detect to read the magnetization. So how this time-resolved magneto-optical Kerr effect works? So it is called a pump probe technique. So there is a pump which is a laser beam which excites, which is an excitation source, which excites the energy of the material. So you have, for example, a metallic system. You have in a certain population near the Fermi level. So if you excite it with certain wavelength, it will take the inner electrons near the Fermi level to above the Fermi level. So the electrons will have certain temperature. So electron will gain certain temperature or energy. Energy and temperature are equivalent, right? So these are called hot electrons because they have higher energy than the Fermi level. And this hot electron population will then do something that I will describe later. So the magnetization will change. Like I showed before, there will be demagnetization. There will be then again relaxation or remagnetization, precession, and all these. And that will be detected by this probe beam. So you have a femtosecond laser. I'm not going to describe how a femtosecond laser works, but you have a pulse laser. Each pulse is less than 100 femtosecond, sort of width, and the difference between two pulses is about 12.5 nanosecond. That depends on the repetition rate of the pulse, and that pulse laser has a very high peak power because it is ultra short. So most of the energy is within that pulse, and its peak power is enormous. So we take a titanium sapphire and 800 nanometer pulse laser coming out of it, and we split the beam using a beam splitter, and the most intense part is sent through a second harmonic generator. Second harmonic generator means it actually creates its second harmonic. That means frequency double. So if 800 is this beam, so second harmonic generator by some nonlinear effect will make it 400 nanometer. Whereas this beam, which is the fundamental beam 800 nanometer, will remain like that, and it will follow a different path, and this 400 nanometer will follow another path. So they are basically like a Michelson interferometer. So you split it from here, and then ultimately you combine them, and I'll show you how it occurs. So basically this goes through a time delay. So there is a delay stage in the Michelson interferometer. You remember the delay stage that changes the path of one of the beams. So here the probe beam path is delayed. Okay. And probe beam is also polarized to a very high degree of polarization. And the pump beam after certain path goes through this, and then you can see they are combined here. So beam comes from here, here it is reflected, here it is transmitted. So the two beams are combined from here. So they follow a collinear path and goes through this, and through a microscope objective they are focused together, and like that. So you can see that you have a nanomagnet or any other magnetic material, the pump and probe beams are focused like that. So you can excite certain region and you can probe that region using the probe beam. The probe beam will detect the Kerr rotation induced by the pump beam. The pump beam will excite and change the magnetization state of the system, and that changed magnetization state will cause a change in the Kerr rotation. Continuously it will be changing the magnetization, and you will read the change in the magnetization with time by reading the car rotation as a function of time. So this is what you do here. So after the reflection from the sample, you take the back reflected beam are collected, and they are sent through glass slide on a CCD camera, which can see the pump and probe beam and the sample and so on with a white light source. Then you use a spectral filter because you only want to read the probe beam. You don't want the pump beam. So you filter out the pump beam, only the red beam, which is the probe beam, which has a change in polarization, which is sent into a detector. And the detector is a polarized beam splitter and two photodiode. This is called a balanced photodiode detector or bridge detector. And under certain if it is perfectly linearly polarized light, and if you put it at 45 degree, the two orthogonal polarization in two arms have equal intensity. So if you take a difference between the two, A minus B, that will give you 0. But because there is a car rotation, so that intensity in the two orthogonal arm will be different, and you will have a finite value of A minus B, which will give you the car rotation. So by this way, you actually read the car rotation. You can also read the total reflectivity, which is just A plus B, so the total intensity. And by that, and by varying the time delay, you change the optical path, and so you can read what is happening with the sort of pump excited system. So this is a real system. So this is the laser, femtosecond laser tsunami. This is second harmonic generator. You can see the path of the pump and probe beam. This is the delay generator. So there is a motorized delay stage and a retro reflector. It is actually covered like that. And then here it is the beam combiner, from where it combines, it goes to the sample, back reflected beam goes to the camera, and from here it goes to the bridge detector. So everything is shown. And the excitation scheme, like I said, it can be electrically excited by using some coplanar waveguide, or it can be all optically excited, like I will describe later. And you can see the detected signal like that. So there is a negative delay. This is a 0 delay when pump and probe arrive the sample exactly at the same time. And then there is a positive delay where probe now actually measure the excited state of the sample, or the excited magnetization state of the sample. So you see a demagnetization, a relaxation, and then precession. This is the real data actually. There's a very high bandwidth and so on. And the detector, like I said, polarized beam splitter and two photodiode. I'm not going to the detail of that again. And this is a non-collinear geometry. This is using a very big laser. This is an amplified laser, very high powerful laser. So in addition to a second harmonic generator, there is another nonlinear optics, which is called the optical parametric amplifier. And that can create a range of wavelengths from 250 nanometer to 2200 nanometer. So from UV to IR, infrared. So that can be used for doing time resolved spectroscopy as well. We do that, and this is a sort of picture, and these are all the time resolution, so on and so forth. So this is the data like I showed you, a ultrafast demagnetization, relaxation, and then precession. So what we can do, this is ultrafast demagnetization, and you can see that after the ultrafast demagnetization, there is a this kind of signal, which is due to a terahertz emission. If you do a Fourier transformation of the time domain signal in the frequency domain, we can see there is a terahertz beam. Actually, this has a 2.5 terahertz frequency. So this is basically a time domain signal like that. So you take out the initial part, and this is the damped precessional motion, but there is a background associated with that. So this background is exponential. So you fit it with an exponential function and subtract it, and then you get this signal. So this is a harmonic oscillation which is damped, whose amplitude is damped. So from here you can find out the damping, and by taking a Fourier transform, you can find out the frequency, which is like that. Okay, so you can find out all these properties. And this is ultrafast demagnetization, and I already explained, but there is something called a 3 temperature model. So electron excites the electrons are excited by the laser above the Fermi level due to electron-electron scattering. That creates hot electron because the electronic temperature, which is like that, it actually increases to about 1000 degree Kelvin. It is called a hot electron. And then there will be thermalization of the spin population using Boltzmann distribution. And this hot electrons excites the spin by electron-magnon interaction. And then the spin temperature will also rise because electron is now transferring its energy to the spin. So it has a phase lag, and spin temperature is slightly smaller than the electron temperature. And then after a certain time, electron and spin transfers its energy to the lattice. So lattice is heating, or sort of energy is increasing very slowly, but ultimately they equilibrate here, and the temperature of the electron, spin, and lattice becomes same. So if you take a system at room temperature, electron, spin, and lattice, they are at the same temperature. But insert under a femtosecond laser pulse in this non-equilibrium region within this time scale, like femtosecond to picosecond, 10 to the minus 15 to minus 12 second, electron, spin, and lattice temperature are different, and that is why they are called three temperature model. Okay, and there are different mechanisms for this ultrafast demagnetization. I'm not going into the detail of that, but there is something called spin flip scattering, and there is something called spin current related effect, super diffusive spin current effect. And I will show you. I don't know how much time I have left. Can you tell me how much time I have left, or do I have any time left at all?
No, actually, you don't have much time because we are about to end at 8:10. So now it is
Okay.
8:23.
Okay,
So
I will finish basically. So I have given some glimpses of how it works, and I will go to the sort of so how we measured some magnetic crystal here using this, and the Fourier transform you can see show different modes, and they have different properties, like they have different symmetry property and so on. And then these are their mode profiles, so how they behave. And this is a magnetic stray field distribution. And then this is Brillouin light scattering, which is an inelastic light scattering. So similar to Raman scattering, there is a creation and annihilation of sort of phonon, magnon, and so on. So you can see Stokes and anti-Stokes peaks, and from here the shift you can actually find out the sort of the energy of the phonon or magnon, or or something like that. And this is a Brillouin light scattering setup, and you can measure different things. There is another exchange interaction which is called the Zyloshinsky-Moria exchange, which is an asymmetric exchange, and that can give rise to chiral spin texture like skyrmions and various kind of spin texture. You can do imaging of the spin wave by using microfocus Brillouin light scattering. And then this is called ferromagnetic resonance, I mentioned before, where you can measure it in the frequency domain. And this is how it is measured using a vector network analyzer and by measuring the scattering parameter. And this is in our lab. So you have a coplanar waveguide, and there are probes by which you launch some RF current or microwave current, and you measure the absorption of that by the magnetic material which is under this conduction line, and you get, and these are different kinds of waveguides for shorted line, these are open line, and so on. And these are like the ferromagnetic resonance spectrum, real and imaginary part. And if you take all of them, make a surface plot, you get a very beautiful pictures like that. And this is ferromagnetic resonance from a bicomponent or a alloy-like magnetic crystal, and we see different kinds of modes, analyzed it, and we can actually use it for faster propagation of signal, on-chip signal. Okay, and then spin orbit effect I mentioned is a pure spin current. This is similar, not like spin polarized current or charge current, but there is just a spin propagation like that. And then how they are prepared, what is spin Hall effect, and so on, and then how it exerts a torque to the system, and how it can replace the sort of the precessional torque or the Oersted field driven torque, and how we detected the spin Hall effect by an optical means, so on, spin pumping effect, and then a little bit of quantum science and technology, how they are merged to give you the sort of quantum science, and different verticals like quantum computing, communication, and so on, and how magnon play a role, or spin-based system play a role here. That is what I wanted to discuss. And quantum sensing and metrology, NV center, magnetometry, and different quantum material and devices. And magnon will play a key role in these verticals, because you can prepare magnon-based qubits, on-chip quantum communication, and transduction, and magnon-based quantum sensing, and different quantum and topological materials. And these are some of our recent results on hybrid and quantum magnonics, which are published in very high impact journals. These are the research activities of my group, different things starting from ultrafast demagnetization to different material. These are indigenously built techniques in our labs. These are photographs of time-resolved MOP, FMR system, dielectric relaxation spectroscopy, femtosecond amplifier lab, Brillouin light scattering, microfocus Brillouin light scattering, sputtering. This is reactive ion etching, e-beam evaporator, cryoferromagnetic resonance, and so on. These are the clean room that also sort of is under me, and you can prepare different kind of micro and nanoscale devices in this clean room and characterize it. And finally, I will acknowledge these are some my student, and this is a stalwart of magnonics. This is we call him the father of magnonics. His name is Burkhard Hillebrand. He visited my lab, and these are my students. Are very happy with him. And these are two books that I have written, and many of these physics and experimental techniques can be found. And both are from Springer. So if you give like Springer and my name, you can find these books, and your library can also keep it. Thank you very much. So now I can take up questions if you like.
Yeah, Manideep, would you like to ask the question on behalf of the students?
Yes, sir. So we have few questions.
Yes.
So the question is why there should be a delay between the split beams in the MBOK microscope, and why it is necessary.
There is a split.
So can you hear me?
Yeah, I can hear. But there is you say something. Why there is a split beam?
Yeah, why there should be a delay between the split beams in the MBOK microscope.
Oh, okay, okay. Time resolved MOC microscope. There is a delay. You said there is a delay, right? So the delay is to change the time delay. So like I said, the pump beam will come and excite the system. So the probe beam will come, even before the pump beam excites the system. So it know that this is the equilibrium state. And then when they have the same time delay, then they will come together. So it knows that now it is exciting. And then pump excites and leaves the system to do its own dynamics. And the probe beam will come. So you have to change the delay, and probe beam will come after the pump beam as well, in order to follow what is happening, what dynamics is actually happening. So this way you can find out the time evolution of magnetization with time. Okay, and that is why there is a delay, optical delay. It is not like Michelson interferometer where you change the delay and there is a collapse of the fringes. It is not like that here. It is excitation, and then the ensuing or the following dynamics is measured like that. Okay. More questions?
So another question. In some papers, the effective magnetic field H effective in the LLG equation is calculated by differentiating the Hamiltonian of the system by local magnetization.
Yes.
Can you explain how that can be done?
Yeah. So effective field, you can take the Hamiltonian, and if you take the gradient of that, actually you don't have to take the differentiation. Basically you take the gradient of that, and that will give you the the energy of the system. This is a simple thing. You can get it from the simple electromagnetic theory.
I think if you have more questions, so you know the Professor Barman's email ID. You can directly contact him also, because
If there is any more very pressing question, you can ask. Otherwise, you can contact me as well. Yes.
yeah. So I just request our head, Dr. Manish Singh. So if he want to make any closing remark.
I'm audible.
Yes, you are audible. I stopped sharing. Yes.
So good evening, everyone. On behalf of the Department of Physics, the LNMIIT Jaipur, I would like to extend our sincere gratitude to our distinguished speaker, Professor Anjan Barman, for the insightful and interesting session on magnetization dynamics from the theory to experiment in our LNMIIT online physics colloquium series. Your interactive and engaging approach made the session both informative and enjoyable. We value the knowledge and useful skills you imparted to our attendees. Your contribution made the colloquium a great success and we appreciate your time and effort. I also thank everyone who made today's session possible, the organizing committee, especially Professor Subhan Viswas, technical support team, and of course, all of you who participated so actively. Your presence and engagement make events like this truly worthwhile. Once again, thank you, Professor Anjan Barman, for being with us today. We hope to have the opportunity to welcome you again in the future in physical mode in LNMIIT.
Yeah, thank you so much. Actually, I have been to LNMIIT probably a couple of times before. I really like your campus, and maybe in future I can also visit your campus. And
so please, sir, please come. And thank you all.
Thank you very much. Okay.
Okay, so here. Okay, so here we end the session.
Okay, so I'm leaving the system. Yeah.
Okay.
Thank you. Bye. Thank you, Shubhan, for
inviting.
Bye.